Let's take a look. The expression of emotions, such as crying and laughing, involves a delicate balance between excitatory and inhibitory neural transmission, and a complex interaction between many neural pathways. However, evidence suggests that the motor response of emotional expression is fully coordinated within the pontomedullary region of the brainstem. These motor responses involve integration of multiple brainstem reflexes for facial, laryngeal, and diaphragmatic movements through signaling with multiple neurotransmitters, including glutamate. Impulses to presynaptic glutamatergic neurons stimulate the release of the excitatory neurotransmitter glutamate. Glutamate works by activating NMDA and AMPA receptors on postsynaptic neurons, triggering ion channels to open. This allows the passage of positive ions into the postsynaptic neuron, depolarizing the membrane and creating the excitatory signals thought to generate the motor responses of emotional expression. This excitatory activity is normally modulated. For example, stimulation of sigma-1 receptors on presynaptic neurons can reduce the amount of glutamate released. Under normal conditions, the excitatory activity that generates these reflex responses is thought to be balanced by inhibitory input from higher levels. Inhibitory signals are thought to travel down the frontopontine tract from the cerebral cortex. Cortical areas are thought to process relevant cognitive and social context for the expression of emotion, and normally send this input to the brainstem center. In addition, it is believed that the cerebellum sends input to fine-tune emotional displays via direct cerebellar projections to the brainstem. The cerebellum also communicates with the frontal cortex, completing a circuit from the cerebellum to the thalamus and frontal cortex, back through the pons to the cerebellum. When functioning properly, this circuit is thought to ensure that emotional expression is appropriate to the situation. However, lesions anywhere in the circuit can disrupt the process. For example, loss of cortical input to the pontomedullary area has been hypothesized to cause the disinhibition of brainstem reflexes, with resulting glutamatergic hyperactivity, which may produce IEED. Furthermore, loss of cerebellar modulation of the thalamus and cortex may dysregulate cortical input to the pontomedullary center.